Dear students, welcome back to your physics class. I'm Mr. Idris, physics teacher at Paris Private School. If you remember in a previous lesson, in section 3, chapter 3, we talked about the wave. So the definition of wave is the motion of a disturbance. Okay? In the wave, the particles do not travel, but the energy is traveling. Okay? So the particles in the wave can only vibrate in its place, but energy transfers when the wave is occurred. Okay, and also in a previous lesson we talked about the types of wave. We have two different types of wave: mechanical wave and electromagnetic wave. Mechanical wave is a wave that requires medium or particles to travel in. Okay, but electromagnetic wave is a wave that occurred and that can pass even through the vacuum when there is no particles, such as the energy light from the sun. Okay, the energy of the light from the sun do not require a medium when it passes through this medium. So we can say the electromagnetic waves can pass through the vacuum. So we have two different types of mechanical wave: transverse wave and longitudinal wave. Okay, but electromagnetic wave has only transverse wave. Okay, so in a mechanical wave we have two types: transverse wave and longitudinal waves. In a transverse wave, such as the wave of the rope when you are shaking, okay, and for example, the water wave also is a transverse wave. What is the difference between transverse wave and longitudinal wave? Transverse wave is a wave that consists of several or series of crest and trough. Okay, it consists of what? Crest and trough. What is the crest? Is the highest point from the equilibrium position. Okay, so but longitudinal wave, in transverse wave, how particles vibrate in a transverse wave? In a transverse wave, the particles vibrating perpendicular to the direction of the wave. For example, when the direction of the wave is in the horizontal direction, the vibration of the particles, it should be in a vertical direction. So that is why the vibration of the particle is always perpendicular in a transverse wave. But today's lesson, we will talk about the longitudinal wave. The longitudinal wave is an example or another type of the mechanical wave, such as a sound wave. Okay, now I'm going to tell you how the particles vibrate in a longitudinal wave. So what is the difference between longitudinal wave and transverse wave? Both of them a type of a mechanical wave. If you see the longitudinal wave, look at this spring. Okay, we have two different regions. This region when the coil is pinched together, and so in this region we can say compression region, because it has more density and more pressure. Okay, so another region is called the rarefaction or stretched region, which has low density and low pressure. In a longitudinal wave, the particles of its medium vibrate parallel to the direction of the wave is traveling. Okay, so in a longitudinal wave, how particles vibrate? Parallel to what? To the direction of the wave. For example, if we have a sound wave consists of, so what is this region? This is compression region. What is this region? Compression region. Okay, so this region is rarefaction or stretched. Okay, stretched or rarefaction region. So in this case, how the particles vibrate in longitudinal wave? In a longitudinal wave, the particles vibrate parallel to the direction of the wave. This is direction of wave. Direction of what? Of wave horizontally. Okay, and the direction of the vibration of particles is also parallel. Okay, it's moving forward and backward. Okay, so in a longitudinal wave, how particles vibrate? Parallel to the direction of the wave. But in transverse wave, in a previous lesson we studied, in a transverse wave, the particles vibrate perpendicular to the direction of the wave. So this is the main difference between longitudinal wave and transverse wave. Once again, listen to me carefully, please. In a longitudinal wave, the vibration of the particle is parallel to the direction of the wave. Okay, but in transverse wave, the vibration of particle is perpendicular to the direction of the wave. In longitudinal wave consists of what? A series of several compressed and stretched regions. Longitudinal wave consists of what? Compressed and stretched regions. So this is another difference with the transverse wave. In a transverse wave, we had creases and troughs. Okay? But in the longitudinal wave, instead of crease and trough, we have compressed and stretched region. So the compressed and the stretched region belongs to what? To the longitudinal wave. Is a part of what? In longitudinal wave. Such as vibrating of spring or sound wave is two main examples of longitudinal wave. What is sound wave? Sound wave is a longitudinal wave. Why sound wave is a longitudinal wave? Because air particles vibrate back and forth. What do you mean by back and forth? It means that the particles vibrating parallel to the direction of the wave. Parallel to the direction of the wave. In a direction parallel to the direction of the wave motion. This is sound wave. So what is compression? Compression is the region of what? Longitudinal or transverse? Compression is a region of longitudinal wave. But crest is a region of transverse wave. Okay? But this is compression, region of what? Longitudinal wave, in which the density and pressure are at maximum. In a compression region, the pressure and the density has maximum value. Okay? Because it is compressed, so that is why it has more density and more pressure. But rarefaction, or sometimes you can say stretch it, okay? There is no difference between rarefaction or stretch. You can say both terms, okay? Is the region of longitudinal wave in which the density and pressure are at minimum, has low density and has low pressure, because in this region the particles are moving away together, okay? We have some notes about the longitudinal wave. Wavelength in a longitudinal wave is the distance between two compressions or two rarefactions. Okay? What is the wavelength in longitudinal wave? The wavelength in a longitudinal wave is the distance between two consecutive compression or two consecutive rarefaction. Such as in a transverse wave, if you remember, we said the wavelength in a transverse wave is the distance between two creases respectively, two consecutive creases or two consecutive troughs. This is the distance, this is the wavelength, okay? But in longitudinal wave, assume that this is compression, this is rarefaction. Okay, what is this? This is a figure of longitudinal wave. Okay, it has two different regions: compression, rarefaction, compression, rarefaction. The distance between two compression, from this compression to the next compression, is equal to one wavelength. So that is why the wavelength in a longitudinal wave is equal to the distance between two compressions, or the distance between two rarefaction is the same. So what about this distance between two rarefaction respectively? The distance between these two rarefaction respectively is also equal to one wavelength. Okay? So let me ask you a very good question. Listen to me, please. So what about the distance between compression and rarefaction respectively? The distance between compression and rarefaction is equal to half wavelength. Okay? Like, for example, when we say in a transverse wave, the distance between crease and trough respectively is equal to half wavelength. This is in transverse wave. But in longitudinal wave, the distance between compression and rarefaction respectively is equal to half wavelength. Hope you understood very well because it is very important and it has been brought in the Wizari exam many times. So please pay attention, okay? A longitudinal wave at some instant can also be represented by a sine wave. So this is very, very important, please. Listen carefully. Can we represent the longitudinal wave as a sine wave? Yes, of course. How? Now I'm going to tell you. Once again, listen carefully. A longitudinal wave at some instant can also be represented by a sine wave. So the creases of the waveform correspond to the compressed regions. The crease corresponds to what? Compressed region. The trough of the waveform corresponds to the stretched region. Okay, so we can say that, for example, if you see this figure, okay, we have two similar figures here, okay? If you see displacement here, displacement or distance or something like that, what is here? Displacement, okay? If you see displacement here, it means that this wave is transverse wave. What is the type of this wave? This is transverse wave, okay? Why? Because here we have a displacement. So the distance from the equilibrium position to the highest point or to the lowest point is present in the transverse wave, which is, we can say this is crease and this is trough. Okay? So this wave is a transverse wave. But the second figure, if you see density or pressure, okay, if you see density or pressure in the figure such as you can see, okay, in this figure, if you see density or pressure here, it means that this type of this wave is longitudinal wave. What is this wave? Longitudinal wave. Why? Because here we don't have distance, we have pressure and density. This point corresponds for what? Highest density, maximum density, or minimum density? This is maximum density. Okay, this is maximum density, which corresponds for what? The compression. Okay, what is this region? Is compression. So what about this? This is the minimum density or minimum pressure. Minimum pressure and minimum density is a region in longitudinal wave. Okay, so corresponds for what? Trough or crease? Trough. Okay, so the trough corresponds for what? Longitudinal. Less density and less pressure corresponds to the trough of the transverse wave in a sine wave. Okay, and also we have one more creases here. So again we have compression. If you look the figure, the crease is in the front of the compression. So that is why the crease of the waveform corresponds to what? Compressed region. Okay? The crease corresponds to what? To the compressed region. But trough corresponds for the rarefaction or stretched region. Again, the crease, another crease, it means that another compression. Okay? So finally we can say we can represent longitudinal wave as a sine wave. How? You can say the crease of the sine wave corresponds for the compression region, and the trough of the sine wave corresponds for the stretched or rarefaction region. Okay, so how can you separate these two figures? Because some of the students they are struggle between these two figures because they say this is the same figure. Actually this is not the same, because we have displacement here. If you see the displacement, it means that this type of the wave is transverse wave. But if you see pressure and density, so you have to say this sine wave is a longitudinal wave. Both of them sine wave, but this sine wave is transverse wave. The second sine wave is a longitudinal wave. Why? Because here we have density and pressure. Okay. Longitudinal wave can often call it density wave or pressure wave. The creases where the spring coil are compressed are region of the high density and high pressure, but the troughs where the coils are stretched and are regions of a low density and low pressure. Look at this figure. A longitudinal wave at some instant can also be represented by a graph, sine wave. The creases of this wave form correspond to the compressed regions and the troughs correspond to the stretched region. As you can see in this figure, this is compressed region. What is this? This is compressed region. Corresponds for what? Creased. But here, this is rarefaction. Corresponds for what? Trough. Okay? Look at this figure. Is this sine wave? Is this sine wave longitudinal or transverse wave? Is this sine wave longitudinal or transverse wave? You have to say this is longitudinal wave. This is not transverse wave. Why? Because the pressure is here. If you see pressure or density, you cannot say this is transverse wave. This is compression, this is rarefaction. Okay? If you draw like in a shape of longitudinal wave, okay? And instead of crease, you have to write down the compression, and instead of the trough, you have to write the rarefaction region. Also, the second sine wave is a longitudinal wave. Why? Because we have density here. Okay, the crease corresponds for the compression. Trough corresponds for the rarefaction. Again, one more. Okay. Why sound waves in the air are longitudinal wave? Because air vibrates back and forth, parallel to the direction of the wave, in a direction parallel to the direction of the wave. So that is why the sound wave is a longitudinal wave. Sound wave is a mechanical wave. In a mechanical wave, the sound wave is transverse wave or longitudinal wave? Absolutely, the sound wave is a longitudinal wave. Why? Because the sound pass through the particles, so the particles in the sound vibrate parallel to the direction of the wave. Right? The distance between any two consecutive or two compressors respectively, or any two consecutively troughs is equal to one wavelength. The distance, as I mentioned a few minutes ago, the distance between two compression regions is equal to one wavelength. What about the distance between three compressed regions, respectively, is equal to two wavelengths? Okay, so the distance between two rarefaction or two stretched regions also equal to one wavelength. But be careful, the distance between compression and rarefaction, respectively, is equal to half wavelength. Okay, the distance between compressed region to the adjacent stretched region is equal to half wavelength. Look at question 17 in chapter review, a very good question. The figure below depicts a pulse wave traveling on a spring. This is spring, okay? If nothing is written here, okay, if you don't see anything here, so, but you can see up, okay, only one pulse, okay? This up is crest. Okay, so this crest is a region of what? The crest is a region of transverse or longitudinal. The crest is a region of transverse wave. So the type of this wave is what? Transverse wave. Okay, because there is no pressure and no density here, so that is why this is just a figure. You have to say this is crest, this pulse is crest. The crest is a region in transverse wave or longitudinal wave. Absolutely, crest is a region of transverse wave. In a transverse wave, how particles vibrate? The particles, you have to say, the particles vibrate perpendicular to the direction of the wave, up and down. Okay? If you see the direction of the wave is horizontal, this is the direction of the wave. Okay, how particles vibrate? Up and down or right and left? Up and down. Okay, when does the particles vibrate up and down in a transverse wave? You have to say when the direction of the wave is horizontal. So, what about when does the direction of the wave, when does the vibration of the particles is vibrating right and left? You have to say when the direction of the wave is vertically. Okay, but as you can see in this figure, the direction of the wave is horizontal, so that is why the particles vibrating vertically up and down. Okay, perpendicular to the direction of the wave. The question says, in which direction are the particles of the medium vibrating? Vertically. Why vertically? Because the direction of the wave is horizontal. Okay. Branch B, this question has two branches. Is this wave transverse or longitudinal? Transverse wave. Why? Because it has crest. There is no pressure and density here. Okay. Question 18, in a stretched spring, if you have a spring, okay, and if you stretch the spring, several coils are pinched together, okay, compressed together. It means that compressed together, and other are spread farther apart than usual. Okay, so it means that we have two regions. The first region, when it is pinched, it means that compressed. Pinched region, it means that compressed region. And the others spread farther. When the spring is spread, the coils of the spring spread farther, it means that this is stretched region. What is this? This is stretched region. What sort of the wave is this? Is this wave longitudinal or transverse wave? This wave is longitudinal wave. Why? Because we have compressed region and rarefaction region. The type of wave is what? Sorry? Longitudinal wave. Question 20. Look at this question. How does a single point, very good question, listen carefully please. How does a single point on a string moves as a transverse wave? The string move as a transverse wave. For example, if you have the string moves in a transverse wave. What do you mean by transverse wave? It has crest, trough, crest, trough. So, the direction of the wave is horizontally, passes horizontally. Passes what? Horizontally. This is the direction of the wave. Passes horizontally. How a single point vibrates on a string when the string is wave moves horizontally? Up and down. Vertically, perpendicular to the direction of the wave. Why? Because in a transverse wave, the vibration of the particles perpendicular has 90 degrees with the direction of the wave. So, how does a single point of the string moves in a transverse wave passes horizontally by that point? Up and down. If I change the question like that, listen to me. How does a single point on a string moves as a transverse wave passes vertically? Okay, if I change this horizontally to the vertically, the answer will be right and left. Be careful. What will be the answer? The answer will be right and left. In this question, no horizontal, but in my question, when I change it from horizontal to the vertically, it becomes vertically. Okay, but because the direction of this wave is horizontally, that is why the single point on the string vibrating up and down. Up and down. Look at this table. It is very important table. Okay, I made for the student. For example, if the student has a bad time in this case, you can understand this table very easy. Okay, the types of the waves: transverse wave, longitudinal wave. The direction of the wave. If the direction of the wave horizontally on x-axis, how the particles vibrate? Vibrate vertically up and down. Look, when does in a transverse wave? When does the particles vibrate vertically up and down if the direction of the wave is horizontal? So, what about if the direction of the wave is vertical, y-axis, how particles vibrate? Horizontal. Right? For the longitudinal wave, we have no problem in this case because it is too easy, because the particles vibrate parallel. If the direction of the wave is horizontal, the vibration of the particle is also horizontal. If the direction of the particles, or if the direction of the wave is vertically, the direction of the vibration of the particle is also vertically. In horizontal x-axis direction of the wave, horizontal. In vertical longitudinal, vertical. It doesn't change. Okay? Now let's talk about the wave frequency or frequency, wavelength, period, and the speed of the wave. What is frequency or wave frequency? The number of waves that pass a given point in a unit of time measured in hertz. Or you can say the frequency is the number of vibrations or number of oscillations per unit of time. This is frequency. Okay? So every wave and all types of the wave has frequency, wavelength, and speed. Okay? What is wavelength? Wavelength is the distance that the wave travels in a unit of time, such as the distance between two creases, the distance between two troughes, the distance between two compression. This is the wavelength measured in meter. Wave period is the amount of time required for how many vibrations? One complete vibrations. Okay? And also in section 2, you have learned what is the period, the time that takes for one complete oscillation. For example, if you release a bulb from the highest point, moving to the highest one in the other side and back to the same position. Okay? This is the period for one complete oscillation. Measure it in seconds. What about the speed? Wave speed, it is the distance traveled by a crease or creases or troughs, okay, or compression or stretched per unit of time. So we can say that the speed of the wave is equal to frequency times wavelength. So this equation is based from the equation when you studied in grade 11 in one-dimensional motion. Velocity is equal to what? X over t. Okay, the distance or the displacement per unit of time. This is the velocity. Okay, so you studied this equation. The distance in this case, we can say instead of delta x, you can write wavelength. Why? Because wavelength is also the distance. Also, wavelength is what? Distance. Distance between 2 points, distance between two creases. Okay? So instead of delta x, you can write down wavelength. Okay? So for one wavelength, we have what? We have a period. If the wavelength and the period is given, can you find the speed of this wave? Yes, of course. Okay? So you can add, you can write here, you can find the speed of the wave by using this equation. Okay, if you remember, the period is equal to what? Is equal to 1 over f. Instead of period, write down 1 over f. Wavelength divided by, instead of period, write down what? 1 over f. Lambda divided by 1 over f. So according math basic, it's going to be flip if you go to the denominator. If you move to the denominator, v is equal to what? Wavelength times frequency. This is the speed of the wave is equal to wavelength and frequency, so it doesn't depend on the wavelength and frequency. Be careful. Okay? This equation does not depending on its quantities which is present in this equation. Wave speed measured in meter per second, frequency measured in hertz, wavelength measured in meter. Look at this question. What does the speed of the wave depend on? Don't say depend on the frequency and wavelength. Why? Because frequency and wavelength changes together at constant speed. In a given medium, when frequency increases, what happens to the wavelength? Wavelength decreases. But speed doesn't change. So that is why it does not depending on the frequency and the wavelength. So, but the speed of the wave depends on what? The type of the wave, which is mechanical wave or electromagnetic wave, okay, and the properties of the medium, liquid, gas, solid, okay, because the speed of the sound in a solid is faster than the liquid and the gas. Why? Because the particles are much closer to each other in a solid state, so that is why they can transfer easily and with a very high speed in a solid state. Okay, so the speed of the sound in the solid approximately is equal to 3,100 meters per second at a given temperature. But the speed of sound in the air approximately at 10 Celsius maybe is equal to 340 meters per second, which is smaller than the liquid and solid. The period of the wave is inversely related to the frequency, and wave speed equals the frequency times wavelength. So the speed of the wave does not depend on the frequency and period, or frequency and wavelength. Okay? When does the speed of the wave changes? When the wave moves from one medium to another medium. If the speed of the sound comes from the air and goes into the liquid or solid, what happens to the speed? The speed increases. Okay? When the wave moves from one medium to another medium, the speed changes. And when the properties of the medium, such as temperature or density, are varied. The relation between the speed of sound with the temperature is directly proportional. When the temperature increases, what happens to the speed of the sound also increases. When the temperature decreases, the speed of sound also decreases. There is a direct relation between speed of the wave or speed of the sound wave and temperature. Okay? A pulse wave, a wave that consists of a single traveling pulse. What is the pulse wave and periodic wave? For example, if you see this, what is this? This is pulse wave. Okay? So, what about this one? Also, this is pulse wave. Okay? But if you see several creases and troughes, as you can see in this figure, can we say this is pulse? This is not pulse. Be careful. This is periodic wave. What is this? This is periodic wave. So we can say the periodic wave consists of several creases and troughes. Or we can say consists of several compression and rarefaction. So what about this figure? If you see this figure, is this periodic or pulse wave? This is pulse wave. Is this pulse wave longitudinal or transverse? This is longitudinal. Because it has only compression. But if you see, what is this? Can we say this is periodic wave? No, this is pulse wave. This is pulse wave. So in this pulse wave, we have only stretched. But if you see many compression with many rarefaction, can we say this is periodic? No, this is pulse. No, this is not pulse. This is not pulse wave, but this is periodic wave. So this is the difference between pulse wave and periodic wave. Periodic wave is a wave repeating continuous pattern which determines its wavelength and frequency, series pulses. Okay? We have some notes about the frequency, wavelength, and the speed of the wave. Frequency depends on what? Depends on the source of vibration. The frequency of the wave does not change by changing medium. Frequency only changes by changing source. Okay? The frequency of the source does not change by changing medium, by changing temperature. Okay? The frequency of a wave changes only by changing source. Frequency depends on the source of vibration, which means that it doesn't change by changing medium. Okay? Note number 2. Wavelength depends on what? Both source of vibration and medium. Is the wavelength changes by changing medium? Yes, of course. Okay? For example, when the wave passes through the air into the water, what happened to the speed of this wave? Increase. What about the wavelength? Also its wavelength increases. But its frequency doesn't change. Which means that the wavelength changes by changing medium, but frequency no. The speed of the mechanical wave depends on the type of medium and the properties of the medium, such as temperature and density. Okay? The product of the frequency and wavelength is always the same at the same temperature and same medium. Okay? the product of the frequency and the wavelength is always the same at the same temperature and the same medium. When the mechanical wave's frequency is increased, its wavelength must be decreased in order to its speed remain constant, because they are in the same medium. For example, in the same medium, if the frequency increases, what happens to the wavelength? The wavelength decreases, because it is inversely related at constant speed. When we say V is equal to frequency times wavelength, if the speed is constant, speed is what? Constant. When does the speed of the wave becomes constant? At the same medium, at the same temperature. When the medium doesn't change and the temperature also remain constant. In that case, when frequency gets higher, what happens to the wavelength? Wavelength decreases, becomes lower, because it is inversely related. Okay? The speed of the mechanical wave is constant for any given medium. Be careful. When does the speed is constant? When in a given medium, in air, solid, or gas. For example, sound waves from different instruments reach your ears at the same moment. For example, when you are sitting in the orchestra, okay, the sound waves from different instruments such as piano, violin, banjo, trumpet, okay, different instruments reach your ears at the same moment. Even when the frequencies of the sound waves are different, the frequency of the piano is different with the frequency of the banjo and with the trumpet, with the flute, okay? Any instrument has its own frequency and wavelength, but all instruments in a given medium, such as in the air, in the orchestra, all instruments, they reaches your ears exactly at the same time, at the same speed. So we can say that the speed of all instruments are equal, but each instrument has its own frequency and wavelength. The frequencies and the wavelength of the sound produced by each instrument may be different. The product of the frequency and the wavelength is always the same. When does? At the same temperature, at the same medium. Okay? The speed of the wave, certain properties of the medium, at the same temperature and same medium. Okay? The speed of the wave changes only when the wave moves from one medium to another, or when certain properties such as temperature and density varies. As the temperature increases, what happens to the speed? Also increases, directly proportional. The speed of electromagnetic wave is constant, always equal to 3 times 10 power 8 meter per second. If a mechanical wave such as sound travels from one medium to another, its frequency doesn't change. Why? Because frequency does not depend on medium. Frequency only depends on the source. If two mediums are the same but different in some properties such as temperature, okay, then its wave speed will be different. In a wave's period is equal to delta t and wavelength is equal to delta x for one vibration. Okay, in one vibration delta t is equal to period. If the distance from the crest or the trough are given with the time interval, use this equation, which is equal to delta x over delta t. Okay, inshallah, in the next lesson, we will continue explaining and finishing this section. Thank you for listening. Keep up your best day. Goodbye.